Hello and welcome to SimScale. In this video tutorial, we will perform a compressible flow simulation over an airplane wing. The objective of this simulation will be to understand the development of pressure on the wing surface and around it, as well as observe the wake propagation using streamlines. This tutorial teaches how to set up and run a steady-state compressible simulation over an airplane wing, extract fluid volume using Cad mode, initialize velocity and temperature across the domain, create and assign topological entity sets to boundary conditions, mesh using the standard algorithm in SimScale and assess mesh quality, explore SimScale's online post-processor to analyze the results. There are two links in the description. One allows you to import the project and perform the tutorial, while the other one is a documentation link where all the steps are described in detail. Let's get started. In front of you is the wing geometry that will be used for the simulation. It is a simplified geometry with no blades inside the engine. This is because we are only interested in the flow interacting with the wing, so no rotating flows will be simulated. So, to visualize the airflow, we need to create a flow volume that acts as a virtual wind tunnel. One method to determine the dimensions for the wind tunnel can be in the multiples of chord length. The dimensions of the chord length for this section of the wing can be determined using the dimension scale. So if you zoom it enough and plot it against the dimension scale, you can see that the chord length is approximately 6 meters. If the chord length is named L, then the upstream should be 10 times L, downstream should be 20 times L, and sides can be 10 times L. The overall height can be approximately 30 times the chord length. Remember that there is no hard rule regarding the dimensions. You just have to ensure that the boundaries of the domain should be far away from the geometry. This is necessary to ensure that the flow near the wing won't be affected by the conditions at the boundaries. Keep in mind that the bigger the enclosure, the better. However, a big enclosure will also increase the mesh cell count. More information about the geometry can be found under Geometry Info, where you can see the number of faces, edges, vertices involved, the minimum and maximum length in the X, Y, and Z directions, and the coordinates as well. Now, let's go to CAD mode and create the virtual wind tunnel. Click on Edit in CAD mode icon. This will take you to the CAD mode environment where one can make changes to their CAD geometry, clean it as per the simulation requirements. We have to create an external flow volume. So under flow volume, click on external and set up the minimum and maximum dimensions based on the multiples of chord length. Click Apply. You can see that the flow volume is such created that its face is coplanar with the end of the wing. Now we need to get rid of the wing, which is a solid, because this is a CFD simulation and we are only interested in a flow region. So to delete the wing, go to the delete operation under body, select wing and apply. This operation will delete the wing. Now we only have the flow region. Click Finish to exit CAD mode. This takes us back to the workbench, and now with the already existing wing geometry, we have a copy of wing. This is nothing but the modifications that we did to the wing geometry and created a flow volume. You can rename it. Save. Now is the time to create simulation. Click on the geometry and click on Create Simulation button. This will open up the analysis type tree, which gives you various choices to select from. Planes fly at very high speeds in the regime upwards of 0.3 Mach. In this regime, the density variations in the fluid cannot be neglected as the flow becomes compressible. Hence, we will choose compressible analysis type. Click on Create Simulation again. You can see that on the left of the workbench is the simulation tree. This is where you define your simulation setup. You have to ensure that each node in the simulation tree has a green check mark before you can begin the simulation run. If you click on Analysis Type, you can see that the Global Settings panel is active. Here, you can define the turbulence model and the time dependency. We are not interested in transient effects, so steady state should be enough. For turbulence model, switch to K omega SST. K omega SST is pretty much an industry standard. It works well near the walls and also in free streams. It also provides a better prediction of flow separation than most other RANS models. Save the settings. Now is the time to assign some materials. So go to Materials and click on the plus icon. This will open up the material library. Select Air and then hit Apply. Since there is only one region that exists in our domain, you can see that the flow region is automatically assigned as volume to the air material. The properties can be kept as default and then just save. Next step is boundary conditions. Before we assign boundary conditions, let's try to understand our domain a bit more. Change the render mode to translucent surfaces with wireframe. Here you can see the wing and the flow domain. This is our inlet. The flow will enter from this side and exit from the other side. This face will act as symmetry face. Toggle on select face for better weaving. So this face is the symmetry face. The top, the side, and the bottom are basically nothing but free surfaces. All the surfaces of the wing will act as walls, where the velocity will be 0. Click on the plus icon adjacent to boundary conditions and start with symmetry. Select this face that is coplanar with this end of the wing. Save. Next is slip walls. So go to walls, change the velocity type to slip. Let the temperature type be adiabatic and assign the top, the bottom, and the side face. Temperature type of adiabatic means that the heat transfer across the surfaces will be 0. Mathematically speaking, the temperature gets assigned a 0 gradient condition. Rename this boundary condition to slip walls. Next in the list is outlet. Our wind tunnel represents an atmospheric domain, so we'll apply an absolute pressure at the outlet. the atmospheric absolute pressure will be of 101,325 pascals. And let's assign the outlet phase. Save. For the inlet, we will include an angle of attack of 3 degrees and likewise directly mention the components of the velocity in the y and z direction. Select velocity inlet. Make sure the velocity type is of fixed value. And what we will do is, to improve stability in earlier iterations, the velocity will be ramped, starting from a magnitude of 11.6 meters per second at the 0th iteration to the final magnitude of 116 meters per second at 600th iteration. More on iteration later in this video. So to enter velocity values in a ramping format, click on this icon, which will open up the table for you. Make sure it is time-based. For a steady-state simulation, the time means pseudo time. Enter the following values. Okay, what this table means is at 0th iteration, the y component of velocity will take this value, while the z component will take this value. At the 600th iteration, the y component will take the value of 6.071 meters per second, and the z value will take likewise. Apply and exit the table. Keep the temperature to 0 degrees Celsius. And don't forget to assign the inlet phase. Save. The final one in the list is no-slip walls, which will be applied to the wing surfaces. To assign the wing surfaces, we'll need to hide the flow region. To do that, select all the faces of the flow region, right-click and hide selection. This will only expose the wing. Now use Activate Box Selection method. Draw a box around the wing, and this will select all the wing surfaces. Now go to Topological Entity Sets and create a new set with the name Walls. You can see that we have created a topological entity set with the name Walls that consists of all the 23 faces of the wing. Now go back to Boundary Conditions, select Wall. Make sure the velocity is of no-slip type, with turbulence wall treated as a wall function, temperature type as adiabatic, and now, instead of individually assigning the wing faces, just select Walls. This will automatically assign walls to this no-slip wall boundary condition. All right, let's expose the flow domain back. So right-click and show all. We are done with our boundary conditions. Let's move one step back to initial conditions. Initializing flow variables close to the expected solution can actually improve the convergence rate and fasten the simulation. In this tutorial, we will change the initialization of temperature and velocity. The initialization will be of global type, which means that the initial conditions we set are for the whole domain and not a specific part of the domain, usually referred to as subdomain. So select velocity and initialize it to the initial value of velocity inlet boundary condition. So if you remember from our boundary conditions for velocity inlet, these were the components of the velocities at 0 iteration. Save. Similarly, for temperature, we will initialize it globally to 0 degrees Celsius. Next step in our simulation setup is Numerics. This is the place where user can define relaxation factors, solvers, schemes for the simulation. In most cases, the default settings should be enough. In our case, we'll just change the number of non-orthogonal characters. Change it to 2. This is done seeking to improve stability. What this does is the pressure equation will be solved correspondingly more number of times, in this case thrice. This can be noticed in the solver log, which will be discussed later. Save the settings. Now go to simulation control, where you can actually control how long the simulation can run in real time and in also iterations. In a steady state simulation, end time defines how long you want your simulation to run. Beyond this, no more iterations will be executed. And the number of iterations actually depend on delta t. So if delta t is 1, which is basically the time step, we'll have 1000 iterations. For this tutorial, end time of 2000 seconds should be enough. Set the write interval to 2000 as well. This means that we don't want to write any intermediate results, but only the final one. Set the maximum runtime to 30,000 seconds. This represents the real clock time, beyond which the simulation will stop. Leave the rest to default and save. Alright, we are almost there. Next step in our simulation setup is result controls. By setting result controls, you can actually observe the convergence behavior of several parameters of interest even while the simulation is running. For a wing simulation, it will be interesting to see the development of forces on the wing. To monitor those, select forces and moments and assign them to walls. Writing the force data every 10 iterations is enough to assess convergence. You must have observed how creating a topological entity set previously for walls helped us save time in assigning them. Save. For a compressible external aerodynamics simulation, other parameters useful to assess convergence can be pressure at the inlet, temperature, velocities, and densities at the outlet. So to track these, let's create some result control items for surface data. Select area average. What this does is it will write down the average values on the faces that we will select. A write interval of 10 will again be sufficient. Change the name to area average inlet and select the inlet face. Repeat the procedure for outlet. This time, select the outlet face. Save. Finally, it's time to set up the mesh. We'll use the standard measure for meshing. This algorithm is robust, pretty much automated, and works almost for all cases. We would want to add the boundary layer refinement manually. So toggle automatic boundary layers off and also toggle physics-based meshing off. Leave the rest as default. Save the settings. Now we'll add some additional refinements. So click on the plus icon adjacent to refinements and start with local element size. Here you can define the maximum target size for the mesh elements. Setting up a maximum edge length of 0.07 meters will mean that the algorithm will try to not have any mesh cells with edge higher than 0.07 meters. Assign this setting to the walls. Save. Now let's add some boundary layer refinement. Select inflate boundary layer. Let the number of layers be 8 with an overall relative thickness of 0.47, which will mean that the overall thickness of the boundary layer inflation that we will create will be almost 47% of the very first cell adjacent to this boundary layer refinement. The growth rate between these layers will be 1.3. The assignment will again be walls because we want to capture the near wall profiles. Save the settings. As a fluid flows around the body, a turbulent region is developed downstream. This region is called wake. Since gradients in the wake are often high, we will create region refinements. To set up region refinements, go back to refinements and this time select region refinement. Set the maximum edge length to be 0.8 and we will assign to a domain that we will create around the wing. This can be done using geometry primitives. Select a Cartesian box with the following minimum and maximum dimensions. Save. Now this takes you back to the region refinement settings. And now you can see the Cartesian box 1 that we just created has already been assigned. In the domain, this box can be visualized here. So this will mean that within this Cartesian box, the maximum edge length of cells will be 0.8 meters. Save. Let's add one more region refinement, this time a finer one. The procedure is same. However, this time the maximum edge length will be smaller. 0.5 meters should be enough. We'll create a similar Cartesian box. This time, you have to carefully assign the second Cartesian box. This box can be visualized within the domain. And if you toggle back the first one, you can see that the second one is pretty much enclosing the wing tightly than the first one. So what we have done is basically we want the algorithm to create mesh which is very fine around the wing and gradually less fine as we go away from the wing. Save the settings. Now it's the time to run the simulation. Go to Simulation Runs. This will open up a dialog box with an estimation of resources that will be consumed. This will depend on your simulation setup and how long you wanted the simulation to run in simulation control. Start the simulation. The mesh will be computed first, followed by the simulation. The status of the job can be tracked here. The mesh takes around 10 minutes to finish. Under event log, you can find the details for the mesh. You can see that we had these many amounts of tetrahedral elements, these many amounts of hexahedral elements, and similarly prisms and pyramids. The total cells are 2.7 million. The region refinements that we had set can clearly be observed. If you zoom in, you can see that in approximately this box, which was our second Cartesian box, the refinements are higher than the Cartesian box 1 that we had created. Now let's have a look at the mesh generated on the wing surfaces. So pick up the faces of the flow region and hide them. Now, if you zoom in on the wing surface, you can see the mesh created. The mesh can be further assessed using our mesh quality feature. Within SimScale, it's possible to visually inspect mesh quality parameters like aspect ratio, non-orthogonality, volume ratio, and so on. Go to Results, and for example, let's select aspect ratio. You can see that the maximum aspect ratio is 8.5, which is a very good value. Similarly, we can toggle on non-orthogonality, and from the legend, it can be seen that we have cells with non-orthogonality as high as 86.67. If you wish to segregate cells, for example, those lying between a non-orthogonality of 80 to 86.67, then this can be done using ISO volumes. So let's say we create a minimum ISO value of 80 and a maximum ISO value of 87. Then this will separate out all the cells lying within this regime. So you can zoom in and see all the cells that have this non-orthogonality. If you wish to, you can go back and refine the mesh in these regions. The simulation takes around 1 to 2 hours to finish. While the simulation is running, you have access to the solver log, where the output of the actual computing algorithm is written down. Remember that we had set non-orthogonal correctors to 2. This resulted in the pressure equation being solved thrice. Similarly, other data from the computation can be observed here. The best part about SimScale is that while your simulation is running, you can access the intermediate results by clicking on Solution Fields, which will take you to the post-processor, or you can also observe other plots resulting out of the result control that we had set. Let's go to area averages and select area average inlet. For the y component of velocity, you can see the ramping up that we had set at the inlet. Similar thing can be observed for UZ. Let's have a look at the pressure development at the inlet. You can see that at the end of 2000 iterations, the pressure is almost converged. For the outlet, let's have a look at the velocities. So the Z component at the outlet converges at 116 meters per second. And the Y component at around 0.26 meters per second. The temperature is around 0 degrees Celsius. Similarly, other values from turbulence can also be monitored. Let's observe force plots. At the bottom, you can see various types of forces and moments listed. If you click on a certain parameter, it gets hidden. So let's hide all those that we don't need. So now we have pressure and viscous forces in the Y and Z direction. The total force in the Y direction is way higher than the force in the Z direction. You can check the final values to compute the forces. This clearly shows that the lift component will be more than the drag. Thus, the purpose of the wing is served. To have a look at some contours and streamlines, let's go to the post-processor. Every time you enter the post-processor, make sure that you are at the last time step and there are no additional filters. So let's delete the cutting plane that's already there. Go to parts color and change the coloring to pressure based. Let's hide all the other faces of the flow domain. We are now just left with pressure contours on the wing surface. If you right click on legend and switch to continuous scale, you can see a much even distribution of pressure. Clearly, the pressure on the top surface is lower than the pressure at the bottom surface. The pressure at the leading edge is maximum. You can also use the inspect point tool to calculate pressure at individual locations. You can also have a look at the pressure distribution around the wing somewhere along the wingspan. So let's create a cutting plane somewhere along the wingspan and observe this phenomenon. Go to Add Filters, add a cutting plane. Its orientation should be in the x-axis. And adjust it accordingly. Set the coloring to pressure. And this will show the pressure above and below the wing. Now, to actually visualize the flow, let's add some streamlines. First, hide this cutting plane. And add particle traces. The source of particle traces are seeds, so we need to assign seeds horizontally and vertically. These settings completely depend on how you want to visualize the flow. Change the render mode to translucent so that the wing is visible. And now, pick position. You'll see some streamlines generated. However, all the other parts are invisible now. To make them visible, toggle on parts color. Make sure the coloring is based on a solid color. Now, select all the faces of the flow region and hide them. Zoom in to see the streamlines around the wing. An animation can also be created. Set the animation type by particle traces and set up the animation speed to a suitable value. Play. This brings us to the end of today's session. I hope you really enjoyed it and learned something valuable. Let me know your thoughts in the comment section. See you next time.